My name's Tim Head, and I work with the ThEC collaboration, and I'm here to tell you about our salt loop. So you've heard a little bit about the ThEC project already from Dr. Tao and Pamplin earlier. What we really want to do is solve the world's problems, and so that's a big thing to do, but we think that we can at least contribute to it, if not solve those altogether. And so Dr. Tao went through these, and we want to find clean energy and water and fix cancer, because those are things that everybody cares about, and we're excited to do that. How do we want to do it? Well, we want to do it by moving molten salt reactors, and in particularly thorium molten salt reactors, forward. So a little bit of an overview about what I want to talk about. So how do we get to thorium molten salt reactors from where we are? And so I want to try and talk a little bit about that. What are we doing, and what are our goals for the next molten salt test loop? What's our current status of the loop? And then I'll talk about the next steps for our test loop, and then look a little bit farther into the future and talk about what we want to do with our molten salt test system, which will be the next thing that we're focusing on. Okay, so how do we get to thorium molten salt reactors? Well, I feel a little bit like we're over here right now. We've got the old car that everybody liked, and we like to think of the MSRE as our old model that's tested but maybe doesn't work anymore since it was mothballed. And we all really, really want this new model. I went a couple weeks ago to the State Fair of Texas and went to the auto show and got to see one of these GTs, Ford GTs, and amazing car. If you want to give me one, I'd definitely take it for a ride. But our new model is the molten fluoride reactors. And so that's where we kind of want to head, most of us. We aren't stuck with that, but I feel like that's probably where that's going to go in the end. But there's lots of different things that we can do to get there, right? And we can take lots of little steps, and some of those little steps that we have to overcome are the regulatory folks. And so I like what Kirk said yesterday in the panel. I think everybody wants to live in a country where nuclear energy is regulated. We don't want people messing around with this stuff willy-nilly, and it's important that it's safe. But we need to be able to work with these people and make the technology go forward. And so how do we do that? We have to be able to make a safety case for our new reactors and be able to convince the regulators that that's a possibility, even if it's different from what they've done for their entire lives. So in order to make a safety case, we need data to compare with simulation. There's tons and tons of simulations out there and very little data to tell us, hey, this really works. So we need to be able to verify and validate the simulations and make sure that we can convince the regulators that, yes, we really do know what we're talking about. To come up with that data, we need better instrumentation. We need to be able to measure the flow of molten salt at high temperatures. We need to be able to measure the pressure of molten salt directly. We need to do the online chemical monitoring that Dr. Pamplin and others have talked about. So, along with these safety things, we also want to still save the world's solve the world's problems. And so, in order to do that, we need to be able to monitor and filter those fission fragments so that we can get out the isotopes we need for those targeted alpha therapies. We need to know more about the chemistry of MSR. So what happens when you dump 30% of your salt is fuel? What happens when it's 15? What happens when it's 5? These are all questions that I don't think are experimentally validated yet, and we've got to figure those things out. We need all the little stuff too. So freeze plugs, flanges, valves, All of these things need to be figured out, and Copenhagen Atomics is making great strides in that direction, and I saw other people from Delft that are also doing similar things, and I applaud you for that, and thank you for your work moving this forward. Okay, so we need tools to solve these problems. So our tool is our molten salt test loop. So we have a bunch of goals for our test loop. The first, we're inexperienced at using molten salt. And so our initial loop, we set up with a nitrate salt, lithium, sodium, potassium nitrate, and we plan to keep the temperature for this salt below 450 C or so. And basically we're going to test everything we can at these temperatures and learn everything we can, and at the same time build toward the next thing. And so that's where we're headed. Once we think that we've learned most of what we can here, we're going to switch gears and move to a higher temperature salt. We haven't decided what that is yet. It might be a chloride, it might be a fluoride. If you have something you need to be tested in a particular type of salt, we'd love to know about it, because we're trying to stay flexible so that we can serve as much of the community as possible. So we want to use this system for a test bed for instrumentation. So in particular, we have some ideas about flow meters and pressure sensors, and we have long-standing nuclear physics experience, and so we're going to put that to use in building data acquisition systems where we can take terabytes of data if we need to and feed that all into something that we can read and make good use of. So along with that, we've got the mechanical pieces, and don't forget there's all the chemical monitoring and corrosion things that need to be solved and studied. And so we're interested in doing as much of that as we can and helping the community move forward in that way. Okay, so let me tell you a little bit about the design parameters of our loop. So here's a picture of it in as it was, I guess, a week ago. The volume of salt that we have is about 19 liters, and there's space in the top for gas of about 7.5 liters. We're currently running about 36 kilograms of eutectic nitrate salt. The side and bottom heaters supply about 10 kilowatts total of power for our pot heat. We also have heat tape that you saw a little bit earlier. I'll talk about more in a second. There's a 3 horsepower motor, drives a centrifugal pump. It runs from 1 to 60 kilohertz. And I'll also talk more about that in detail here in a second. So the pump is made of 316 stainless, and so are all the pipes and fittings that we're using. We have had a little bit of trouble with the pump. So here's a picture of it as we're putting it in. And so we ended up having to modify it from its original configuration. So here's a picture of the impeller. It actually took us a couple iterations to figure out, but we were having some trouble with resonance. And so you'd get to a certain speed and the thing would start shaking violently, and it would make sounds and make everybody run away. But what we found was, well, the impeller is not balanced. And so we sent the impeller back. Well, that's an easy enough fix, right? Well, it turns out that wasn't all. That is not what you want your shaft to be doing at all. And so what we found was, after quite a bit of work and surprise, that the shaft for the pump was actually not round. And so not exactly what you expect when you purchase a pump like this, but yeah, so the shaft wasn't round. We went to a bigger shaft. because this is a cantilevered shaft, so the bearing support is a good 2 feet above the impeller. And to make sure that we didn't have this problem again, we asked to replace it with a 1.5 inch shaft instead of 1. And that fixed it. So that was good. This is one of the trials we went through. The loop itself, about 7.8 meters of 25 millimeter pipe, so 1 inch for those of you from the US. So in this loop system, we're testing unions and 3 valves and a Krona 4400 HT flow meter. This is the highest temperature flow meter that we could find. For 2-inch pipe, they claim it'll go to 600 C. For 1-inch pipe, they ratcheted down their claims to about 400 or 450. So we'll see what it can do. We're excited to get that going, but it actually hasn't worked yet, so more on that in a minute. So we're testing several different sealants in the threads just to see how threading works. And so Teflon, of course, we don't expect to go very high. We're trying out this graphite stuff, so it's a mix of graphite and something else that goes a little bit higher, and then this very high temperature sealant that we're interested in looking at. So another thing, let me just point out, another thing that we found when we were working with the water in this system, so we sort of characterized our system with water, and in initial tests, what we found was, it's very hard to see here because it's gray, but there's a gray pipe that runs right here and down from the return side of the loop. So the silver looking one is the input to the loop, and the fluid goes around and down through the return. And so initially we didn't have this pipe here. And so the salt came in and it splashed down into the pot and was there. And so what we found though was that made lots and lots of bubbles. And so it sounds like bubbles may be good sometimes. So we're interested in that for filtering things and maybe getting a hold of some of those fission fragments. But in our case, it was causing the pump to cavitate, and that's also a problem. And it also, if you're using an ultrasonic flow meter that uses non-Doppler methods, is a problem. And so these time-of-flight flow meters need less than 2% of bubbles or other trash, let me say, in the path. And so it's very difficult to get these things to read if you have a lot of tiny bubbles floating around. And so what we did was extended this pipe down into the liquid molten salt, and this has solved our problem with bubbles. It introduced other problems, and that's why we have a valve up here to solve the same problem that we just spoke about, of getting air trapped up there in the top. Okay. So we also have heat trace around the loop. There's about 4 kilowatts there of heat trace. As Dr. Pamplin said earlier, these are just wrapped, and there are sections here that are wrapped in aluminum foil to help spread the heat more evenly. We were interested, this was the first time we had run all this together, so we were interested in seeing how different things looked and how they were acting. And so not everything is covered. Of course, we plan to insulate this as well. This was our first run, so we were looking for leaks. And we didn't really want to ruin all of our insulation because all of the joints decided to leak at once. And so we left off the insulation for the first run. Okay, so we also are monitoring everything. So we're keeping as good of tabs as possible on our heat at every point in the loop. We have about 23 thermocouples mounted directly to the loop itself and a bunch more everywhere else. So we're monitoring bearing temperatures and motor temperatures and every other temperature in the room. Even we had some concern from folks in the safety office at the university that we might set off the sprinklers. in the room. And so we've got thermocouples up on the ceiling monitoring temperatures near the sprinklers. So we also have a gas blanket system made to help us dry the salt and to use as a cover gas. This is a quick schematic of what our gas blanket system is. For the current system, we're using nitrogen as our gas blanket. That might change to argon or helium or something else that someone wants very easily. So we have, So we have a supply here, goes through a humidity sensor, and through some set of valves and into the tank. And we also have a release valve here. So since we have both of the sides of the loop are actually beneath the level of the salt, when it's molten, the salt gets stuck in the loop if you don't have this way to release it. So we have to put pressure in at the top of the loop, and that lets us push it out when we're ready to stop. Maybe that's good. So we also have a DAC system. Our DAC system is based on the Midas system developed at Triumph and PSI, and has been used for slow controls for physics for many years. You can monitor many things all at once, and it works very well. We've got some programmers, and so we add things to help us understand exactly where temperatures are different or what parameters we're really worried about. And actually there's 3, besides just this, which is a screenshot of the screen we were looking at to control the loop. We also have 3 big monitors around the room so that we can monitor critical processes at all times. Okay, so we characterized the system with water. We started with just a basic off-the-shelf flow meter. We put that in line with the Corona high temperature meter, and we also did the simple thing, right? We pumped water into barrels and weighed it and said, okay, well, what's the mass as a function of time? Look at that slope, and so that gives us a flow rate. So it turns out we were very glad that we did that low-tech thing, because we had some calibration issues with our very expensive flow meter. So there's the acoustic one, and here's our barrel setup. And here's the flow rate. So if you just plot mass flow into barrels versus what we got when we originally got our chronometer, you can see that wasn't the 1% claimed accuracy of this meter. And so let this be a warning that you should test things. They don't always work like they say they do. So after, I don't know, it was several weeks of back and forth with this company, we did get it fixed, and they just typed in a wrong number at the factory. So nothing really wrong, just something annoying to cost us some time. And so we measured flow versus pump speed, and also differential pressure versus pump speed. And so this was exactly the same setup that we have currently for the molten salt, except we drilled 2 holes in some of the pipe sections on the input and output side of the loop, and measured and placed transducers there for water, and measured those. And then we replaced them with whole pipe sections to when we went to salt. Okay, and so putting those together, we have a differential pressure pump curve that we can hand off to our colleague, Robert Brown, who does CFD. And he has all of the measurements of the loop, and will model this for us and compare his results to our experimental results, and then we can apply those things to salt and make sure that we know what we're doing. Okay, so we have pumped salt, and how do we know? Actually, when we turned it on, the flow meter read 0. That was unfortunate and surprising, but I think I have an idea of why that is, but we still could tell that we flowed salt. When we turned the valve here to open the loop, we had a precipitous drop in the temperature, and it was dropping so fast we were worried that it might freeze on us, and so we turned up the set point to the heaters to add a little bit more heat, and so that's what this little blip is, where we were sure we were melting salt and getting it back around the loop. Another evidence is that we actually sampled salt, and you heard about this earlier in Dr. Pamplin's talk. So we opened this valve while everything was pumping, and we're able to get salt out in its molten form. Okay, so lots of things that we're looking to develop or test. We're looking at Corona flow meter. Sporian Microsystems has a website that says they have a high temperature flow meter, but we haven't been able to get our hands on one yet. We'd like to test that. If there's others out there who have things that they want to test, we'd love to try and test those. We're working on designs of our own for high temperature flow meters to measure average flow rates, but even better, it would be great if we could come up with a design to measure the cross-sectional flow of these things, and that would really help the CFD folks to understand what's going on in the reactors. So we're trying to move that way too. We're looking for pressure transducers and designs for those so that we can directly measure pressures of molten salt. And of course, we're looking at DAC development. And so we recently received a grant from the DOE to develop the DAC for the scientific instruments at the Versatile Test Reactor that's just been approved. Our Congress can do something occasionally. And so that's been approved, and so we're moving forward with those designs. What are our next steps? So impurity analysis. So a lot of these things you've heard about earlier. We're looking at sound velocities and viscosity measurements and building up a catalog of these things for different materials and different mixtures of salts so that whoever needs them can use those. And so we think that's an important contribution to the community. We're also interested in testing mechanical things like valves and filters and freeze valves and whatever else needs to be tested. So then we'll move to a higher salt, likely FLINAC at this point, but maybe not. Give us a reason not to do that, and then we'll look. So once we're done with what we think we can get done with the molten salt test loop, we plan to make a bigger one. And so the next step, move from 20 liters to 200 liters. And that gives us a step in the direction of what kind of volume you might need for a reactor. And so this is just a very preliminary kind of drawing. We would want in situ purification of salts. And a few of the goals for our next system. We want it to be about 200 liters. We want it to be modular so that we can plug in and out different things to test. We want it to have a freeze plug that's integrated, a salt cleaning system, and optical access to try libs or any number of Raman or any number of optical techniques. We think that's very important. We want test sections for instrumentation and hardware testing, and we also want to prepare ourselves to go to the next step and build a full-scale non-nuclear prototype. Okay, so that's a whole lot. I hope that I haven't bored you too much. Thank you very much. I want to thank the people who have funded this work, and especially to my colleagues and the students. Notice they're undergraduate students, so we don't have a lot of grads to work with, but we do have a pretty good pipeline of undergrads, and we love working with them, and it's great. So among the things with saving the world, I think almost half of our goal is probably to teach undergraduates and help them get started. So thank you very much.
Any questions?
Everybody is too tired.
Yeah, we have one up there. Why go for a full-scale nuclear, non-nuclear model?
Yeah, so I think on the, this is down the road, this isn't the next step, right? This is 2 steps away. And I think to convince the NRC that these things are really safe and we know what we're doing, I think this is probably going to be required.
Why then full scale? Why not half scale, third scale?
Maybe that's the answer. I don't know. But I think the handling of that amount of salt and the quantities that need to be used will probably require a full-scale test.
So the full-scale testing is not related to the thermohydraulics, but more to the experience with a large quantity of salt?
I think it's both.
Then I would suggest you have a look at the APEX experiments, which were half-size or downsized experiments for the AP600.
Okay.
You don't have to go to full scale. Use similarity laws which exist in thermohydraulics. If your argument is we need to have experience with large quantities of salt, then I fully agree.
Okay. Thank you.
Well, then you have to have 2 scales because you've got to prove your similarity laws, at least from one scale to another scale. Otherwise, they'll say, well, how do you know similarity if you haven't proved it? So I'm just saying, being a regulator.
Okay. Thank you.
I have a question of you. So you mentioned you have a lot of students.
Yes.
That's exciting. Do you have undergraduate courses on molten salts, or how's it working?
Not yet. I think there's enough of us interested in it that that might develop soon. But yeah, there's nothing yet. Thank you. Yep.